Yep. Uh-huh. Uh, I will cover that in just a second. Yeah. All right. So we'll get to all of that. So I think I got all the sort of prepped in the announcement here. Um, so let's tab over to PowerPoint here. Yeah. All right. So just as a reminder, due Sunday night, your muddiest point. Final projects due tomorrow, Wednesday night. There's no real grace periods here because I have to get the peer review assignments out there. So get them all in Saturday or Wednesday night so that I can get the peer reviews assigned so that everyone's got Thursday, Friday, and Saturday to watch a presentation and read a report so they can submit their peer reviews by Saturday night. Student evaluations are due soon. I actually think it's like one of these weird things where it's actually due like Thursday night and not Friday night, like you might expect. So if you're interested in submitting a course evaluation for the course, there is a link. If you go to Canvas, it's sort of in the nav bar, kind of on the upper left. So it's a quick link to it. You can access it there. You should have gotten some emails about it too from ASU. So the final exam. So individual stage one exam technically is Thursday, but it's actually going to become available Wednesday. So you'll have all of Wednesday, all of Thursday, and all of Friday to do the stage one. It's a 90-minute exam, just like the midterm. So it's designed to be, well, it's designed to take an average of say 40 minutes, and to fit within a 75-minute class period. I just make it 90 minutes for technical issues. So you can start at any of those 3 days, but then you'll have to finish it within 90 minutes, just like the midterm. So you got those 3 days this week, Wednesday, Thursday, and Friday. Then stage two is during finals week. Technically, it's due Thursday of finals week, and you can come to for either one of these. So Thursday, you can come to class during the normal class period and work on your stage one here. You can either use these computers or you can bring a laptop. I'll be here proctoring, but it's just a Canvas exam. And then Thursday during our exam window, which is on the Canvas calendar, you can come here next week during finals week if you want, but you don't have to. I will be here or the TA will be here. So just sort of being a warm body in the room. But if you want to come here to do your collaboration, that's totally fine, but you don't have to. I am making the stage two available all week, Monday, Tuesday, Wednesday, Thursday, and Friday. So you can work on it continuously through the week, or you can start it whenever you want. It's not a timed exam. Again, it's just like the midterm. If you submit multiple versions, so you submit one and then you go, shoot, I wanted to go back and make a change on that, that's fine. You can resubmit. It will grade the latest copy, not the highest scoring one. So make sure that whatever you submit, the latest version of it, that's the one that you want it to be scored. So I think that answers the due date. Does that answer your question earlier then? Great. It's a cumulative exam, all of the units, A through G, comprehensive. You can see in the top of each unit, learning outcomes or sort of a study guide for each unit. You can also find sample final exams from previous semesters available in the final exam module, although you'll need to do that final exam Lockdown browser compliance test first in order to get access to that module. You get one double-sided sheet of handwritten notes, and you'll need your ASU ID when you take stage one to flash it in front of the camera. So just as a reminder of that. And if I didn't say it already, if you want to bring a couple of sheets of blank paper, then that's fine as well, or use a couple of sheets of blank paper. I don't know if you really need it, but if you want to, just in case, that's fine. So one double-sided sheet of handwritten notes and 2 blank sheets of paper. Okay, and so that is the general notes. So I'm going to talk about the final exam in particular, but are there any sort of questions about the schedule or when things are due? Does all that make sense? Questions online as well? Okay, so like I said, it's comprehensive final exam, same format like the midterm. In fact, even the same length as the midterm because they're both designed to fit within a single class period. So even if I don't remember how many final exam samples I have from past semesters, if you go back far enough, you'll find final exam samples that were designed for a full 110 minutes. But when I switched to two-stage exams, it forced my final exams to go to this the smaller format. So it's, the length of the midterm. So I forget how many points. I think the midterm was around 35 points or something like that. And that's going to be about the same as this final exam as well. So that's the type of length you're expecting. So very similar to the midterm. Like I said, comprehensive, about the same length of the midterm, designed to fit with the normal class period. The rest of the way I've got organized today, we can go into or not. So basically what I've got behind this slide is the greatest hits of these slides from these units that we've covered from A through G. I've just kind of arranged them so the post-midterm units are first, and then the pre-midterm units, if we have time today, are kind of after that. But if you have specific questions you'd like to go over, problems you'd like me to work, anything like that, we can do that instead. You can interrupt me at any time and we can do those things. You can ask the questions now, you can ask them later. If I cover the thing and then I go on and then you come up with a question, you can, it's fine for us to go back. It's however you'd like to use this time. So with that in mind, are there any sort of burning questions that anyone has that they want to make sure they get out of the way before the exam window opens up tomorrow? Either in class or online. Nothing, okay. Or in that case, again, as you have questions, feel free to submit them or raise your hand or whatever. But I've just kind of set these up to be like an appetizer to sort of just kind of get thoughts going. So if these generate questions, let me know. Otherwise, we can just kind of move through them. If there's a question that comes up that's unrelated, just again, it's totally fine to interrupt. So if we go back and think right after the midterm, then we started in Unit E, and this is where we started making sims a little bit more complex and a little bit more realistic. And so that's when we introduced things like delays, smoothing and averaging, lookup tables to specify the kind of nonlinear converters, units, sliders, and then starting to, adding causal loop stuff to the stock and flow diagrams. We used some basic kind of case studies to sort of examine what these more complex models might look like. And so the SIR model, we showed the classic SIR model and how it is built, as well as embellishing it to add kind of a quarantine scenario planning. And then we showed how the SIR model is very similar to the BAS model of market diffusion. And so showed how various limited growth models can kind of be stretched to fit different application spaces. So that's kind of like, the sort of the big things there. So those are the kind of the main things that I feel like are really covered in Unit E. If I want to go into sort of some of the specific kind of hits that I can think of from slides from Unit E, knowing about lookup tables, I think is definitely an important thing. I think hopefully we've seen now that you're going to final project, that lookup tables provide a very flexible way to map one set of inputs to outputs without having to come up with a mathematical formula. They're called lookup tables because instead of taking a number and calculating an output, they are used to look up the right output for every input. It's kind of like a little Rolodex of outputs that are keyed by the inputs. In Insight Maker, they're called converters. So, we actually experienced lookup tables as early as chapter 1. So I would say, because we keep using the fishery as like a go-to example, I would definitely know this basic fisheries model and how this net regeneration curve works. So it is a lookup table for one, but it also is just generally a hump-shaped net regeneration that fits within this basic feedback loop. So being able to kind of understand how this relates to the eventual S-shaped growth, and then all the tipping point stuff and all that we got through that sort of happens all around this point right here. That's definitely something I think you should probably know going into the final. But if I focus just on lookup tables, we can think of this regeneration curve as an example lookup table where every corner, every point here gets put into a list, and then all of those points, those XY points, get a line that connects them. And that allows us to map any density that pops up during the run of the model to the corresponding regeneration rate, which then will cause fish to grow or shrink, depending on how big the regeneration is and whether there's an outflow. In this case, there's no outflow, so it just affects how quickly they grow. And that will change the density. So at different densities, you'll get different regeneration rates and so on and so forth. So as the densities get higher, the regeneration rates grow, and then eventually, once it reaches critical density, then shrink due to crowding effects. And the lookup table captures that without us having to build a mathematical expression for it. So are there any questions about lookup tables? Really feel pretty confident about lookup tables. This is traditionally one of the more difficult topics in this class, the lookup table. Questions online? All right. So we know that we encode lookup tables in Vensim. I'm going to show you how to do these, remind you how to do these in Vensim and InsightMaker. I'm not, the final exam may have some questions, basic questions related to Vensim and InsightMaker, but they will be things that are sort of shared features of both. It's not meant to be a practical exam about Vensim because some of you use InsightMaker and vice versa. But I do hope that when you leave this class, you're able to pick up any system dynamics modeling tool and generally kind of know, just like you can get into any car, once you learn how to drive any car, it takes you a minute to figure out where things are, but you can hopefully drive any other car. And I'm kind of hoping that I could be able to ask you generic questions about how system dynamics modeling tools, InsightMaker or Vensim work, and you'll be able to answer those. But specific things like exactly which menu do you go in to find X or Y or Z, I'm not going to ask you that, but it'll be more like if I showed you this diagram, hopefully you'd be able to process this. Like, you can say, oh, this is a lookup table. There's a table of all its inputs. I understand what's going on here, even though I used InsightMaker. InsightMaker had a slightly different version of this, but it had basically all the same info. So that's the type of knowledge that I'm hoping you'll get about the software. So in Vensim and similarly in InsightMaker, you can draw your lookup tables. You've got the tables here and specify them instead of an equation. Manually enter or click them in there. With InsightMaker, it's a similar deal. And then with Vensim, we can also bring time. So that's kind of an important thing, is that sometimes we use time as an input to our variables. And a lot of times we use time as an input to lookup tables if we've got some non-trivial pattern that is a function of time. And so in InsightMaker, we do that with in Vensim, we create shadow variables, and there's a time shadow variable, which then we can bring into lookup tables. And if we take them as an input, then that allows the lookup table to represent some pattern over time. In InsightMaker, time is actually one of the sources. So you can either choose an input that has been drawn in, connected with a line, so like a link, or if there's no length, or you just decide that you're not going to use those links, you can say your input source is time instead. And that becomes the x-axis of the lookup table. And so InsightMaker, same deal. You put in points. You can specify linear interpolation. You can also specify none. So that way you get these lookup tables that are a little bit more box shaped. You can draw these in Vensim, but you got to specify every corner manually. But otherwise it runs about the same way. And so that's your InsightMaker lookup table. So any questions about lookup tables in Vensim or InsightMaker? Yeah. Yeah. So do you want me to go back to the Vensim or? Yeah. So the only way to get time as an input to a variable in Vensim is to create a shadow variable. And remember, in Vensim, shadow variables are just aliases. So they're just kind of like visual copies of other variables in the system, as well as some hidden variables that otherwise aren't showing up on the canvas. And so time is one of those hidden variables. So if I click shadow variable and click here, it pops up a little box here, and I can select that I want time to go there. And that becomes a variable that I can make use of. So I could actually use it in a mathematical formula as well. But in this case, I'm bringing it into a variable that I then internally define as a lookup table. And so in the lookup table, so if I were to go, I don't think in this review, I don't have the, so it's kind of hidden back here. I skipped over it, but in the box where the as graph lives, you specify the input to the lookup table, and you can specify that as time. And then when you click on as graph, then this x-axis to the lookup table will be interpreted as the time variable, which which just marches along to infinity, instead of another state variable within the system. Does that make sense? Any other questions about lookup tables or shadow variables? And again, I should emphasize that shadow variables aren't just for this. You can use shadow variables or ghost primitives in InsightMaker just to kind of clean up your canvases so that you don't have to have wires drawn everywhere. So if you had another set of stocks and flows down here, and you didn't want to draw a bunch of wires from these variables down to here, you could put shadow variables down here. So savings account balance would show up in two places. It would be, they'd be tied together as far as Vensim or InsightMaker were concerned, but they would be depicted visually as two separate entities so that you didn't have to have like long strings of wires going across the canvas. So the major point of shadow variables. Okay. All right. So that was kind of the first thing we started with, lookup tables right after the midterm. Then we got into delays and the two major types of delays. And some of you are now using delays in some of your models, and that's great. So I can summarize the two types of delays with this intersection example. So I've got an intersection A, an intersection B, and a city block that's in between them. And so we can imagine that if cars are waiting at a red light, once the red light turns green, there's going to be sort of a spring kind of spreading out, allowing the cars to fill the city block at the normal distance between them. So they're kind of compressed together like a slinky pulled together, or I guess a compression spring pulled together, and then they stretch out into their normal steady state distances at their city block speed. And that stretching process is the smoothing delay. So the idea here is that the light turns green at time 1, and the cars don't actually enter the intersection all at once. The front cars enter it immediately, and the back cars take a little bit longer to speed up. And so you get what's referred to as a step response of cars entering the intersection until eventually they finally come to their sort of steady state value. And then if there was a red light back at this intersection, then the block would eventually empty in a similar process. And so you have to wait for the cars to empty out of the city block before the block gets empty. So the cars at the front of the block get out quick. The cars at the back, they have to drive across this whole thing. So this is characterized by the average amount of time it takes for a car to get into the city block. So that's what we refer to as a smoothing delay. But once a car is in the block, it takes about the same amount of time for every car to get across the block. And so that delay going from the front of the block to the back of the block, or from A to B, we refer to that as a fixed delay. And so it doesn't change the shape of the traffic at all. It just moves the traffic from one point in that same shape to another point. And so those are two ways that we can delay things in our dynamical systems models. So any questions about the two types of delay, smoothing and fixed? I've got examples, fixed delays. So fixed delays, schooling behavior, age structure and population. So there are 50 kids in kindergarten. So next year there'll be 50 kids in first grade, and so on and so forth. So it doesn't change the structure. It just whatever the number was the year before, it gets pushed on the year after. Students moving through school system. Material flow. There's so many items on a conveyor belt. Conveyor belt moves, and so a little bit later, the conveyor belt brings all of those items to another point. So transit delays, material flow, these are all examples of fixed delays. Smoothing delays, I gave that example of the traffic flow. We also talked about, like if food enters the stomach, all of the nutrients from that food, some of them enter the bloodstream quickly, the rest of them enter them slowly. And so this idea of the food being processed sort of at, I don't want to say different rates, but some of it being taken in earlier than later, that's a smoothing delay. And so the input changes instantaneously, food enters the stomach, but the blood actually doesn't feel it until later. And when food exits the stomach, there's still some that's in processing in the lining of the stomach. So you continue to get some absorption into the blood until eventually all of that empties out. This is sometimes known as exponential damping or exponential decay. It's the same process we talked about water filling in the toilet and then water actually emptying from the toilet. We talked about the delay that we characterize here is a measure of the sluggishness of the system, how much distance there is between this red curve and this blue curve. And so more stubborn systems are more sluggish and they have higher delays, or in other words, this red curve is going to be shallower and shallower. So the index we use is the time after the step where the system reaches 63.21% of its final value. And so if its final value is the top of the step at 63.21%, somewhere around here. So this is our step response down here of about 2.5 seconds. So it takes 2.5 seconds for the red line to climb to 63.21% of that top line there. That funny number, 63.2%, we choose that because if we choose that number, it has the nice interpretation that it is the average delay a small unit of the thing being processed feels. So I mentioned that some food gets into the bloodstream immediately, the rest of it has to wait. Well, if we look at all of those little food bits that are getting turned into nutrients in the bloodstream, then we can average across how long do they have to wait. And the average time across that, where some get processed immediately and some take a long time, will be this 2.5 seconds. And so it just so happens that with these exponential decays, that the average waiting time also corresponds to the time that this curve reaches 63.21%. It just comes out of the math. So that's why that's a special number. So any questions about smoothing delays? This is also called the time constant. So know that term, time constant, that if I talk about smoothing delays, I might refer to the time constant, and that is just the index of the sluggishness of the smoothing delay. The time at which the step response reaches 63.21%. All right, no questions online. Okay. So, it's a little exercise in that. We did this one earlier where it's hard to see this thin blue line, but there's this blue line that rises up here. This green line is the input. And if I wanted to guess what the time constant of this system is, I go up to around 63%, and it says it happens around time 3, but the step happened at time 1. So I would say the time constant of this system is 2 seconds. So questions about that? Feel pretty good about those 2 delays? Okay, so we don't have to build this ugly stock and flow diagram whenever we need to build a delay. Instead, there are, so basically I'm going through, again, I just borrow some of these stats, so I think I'm going to maybe jump ahead. So all of these slides are the slides I borrowed when we're talking about delay, me sort of emphasizing that this time constant represents sort of an inertia in a system. So whenever you've got something which a little bit changes immediately, but it takes a long time for the whole thing to change. So it's kind of like, people's minds don't change overnight. They kind of change gradually. And how quickly people's minds change, sort of, it's how stubborn they are or whatever, it's sort of an inertia in those systems. And so we generally refer to systems that behave this way with this kind of sluggish response as systems that have inertia. And a time constant is a general way for us to measure the inertia of a system. So I mentioned a couple of examples here: stubbornness, bucket diameter, heat capacity, mass. All of these things would relate to something having a high time constant. And that's all they're kind of saying here. So what I thought I was getting to here was we have these formulas, smooth and delay, in Vensim and Insight Maker, that allow us to quickly do those delays without having to write those out. But apparently I got ahead of myself there. So are there any general questions then about fixed and smoothing delays? Yeah, I can go back to and get my mouse back here. There it is. Say here. Question? No, well, you can do a step response and a fixed delay, but instead of the output being this red line that rises up smoothly like this, you'll get a copy of the step that will jump up later and so it'll just look like you took the blue step and shifted it over 2.5 seconds. So a fixed delay is like the purest form of a delay. It's like a true delay. Whereas a smoothing delay is like, it's somehow like a weaker delay because you allow some of the system to respond instantaneously where the rest of it responds really slowly. And the average behavior is characterized by this time constant. And so that's kind of what we're showing here. Now, I've mentioned that there are higher order smoothing delays where you can chain together smoothing delays that have like two smoothing delays, each with half the time constant, or three smoothing delays, each with a third the time constant. And if you do this process, then if you have like 100 smoothing delays, each with 100th the time constant, you will end up recovering something that looks almost identical to a fixed delay. So instead of being a smooth response like this, it'll be flat, and then it'll have kind of an S-shaped, like a very steep S, where it'll rise very quickly, and then it'll level off very quickly. And so these higher order smoothing delays are the in-between. So if you want something that isn't as sharp as a fixed delay, but doesn't respond immediately, then you use a higher order smoothing delay. And the amount of the order of the smoothing delay, a second order, a third order, whatever, has to do with how fixed like you want the smoothing delay to behave. So that's kind of like the spectrum of delays: fixed delay, smoothing delay, higher order. So the higher the order of the smoothing delay, the more it gets like a fixed delay. Yep. A step response is a process by which you excite a system's input with what we refer to as a step. And so you just make something rise to a constant value, and then you watch how the system responds. So in a toilet, a step response is like flushing the toilet. So when you flush the toilet, then you basically turn off the process temporarily, or I guess you could say if you empty the toilet, then at the point where the toilet's empty, then it's like the toilet wants to be full, and we can measure how quickly does it actually become full again. So the input there was, the toilet's empty. That's the input. The input is like, I want you to be full, but you're empty. So it's like you've gone from being okay with the toilet being empty to wanting the toilet to suddenly to be full, and then watching how quickly it responds. So a step response is a way in which we can characterize how real systems are, the sluggishness of real systems. Mm-hmm. And so people do this on a, like, if you've ever, watched, there are engineers that have done this. So like, if I go over to this door and I open it up and then watch how quickly it comes back, that's been designed. Like the speed of that door has been designed. And the way, so there is a spec for this curve up here, for that hinge, basically, that actually specifies how quickly it's supposed to come back. And they've used a step response to characterize that. So you can think of, if I open this door all the way up to 90 degrees, and then I let it close, I can measure how long it takes for that door to come to 63% of closed. And that time will be the time constant that has been designed into that hinge. And so mechanical engineers know what types of things to put in this box to make that system slower or faster. And they can tune those to make the step response have the specified time. Okay. Any other questions about these delays? So let's go jump back to. All right, so kind of towards the end of the unit, we got out of Vensim and InsightMaker and looked at the sort of examples, the SIR model. SIR model is just so fundamental. I want you to know basically how this three stock multi-compartment model works. So that if I just could ask you, what is the process going from infectious to recovered, that, well, that's basically just a time constant there, that it's just the number of infectious or decaying into recovered with a certain time constant. So basically, it's good to know this this basic structure here of the SIR model with its different feedback loops. You've got the S, the I, the R. The I to R is basically the bacterial outflow type model. And then, the S to I is this kind of stage structured model. I'm not going to ask you to write the formulas out, but I might ask you, if I gave you a portion of this model, I might ask you to choose among expressions that would make sense for particular nodes of these. And so you'll be able to have to reason through based on the units, based on what's going on, what makes sense for dangerous contacts per day, things like that. So if we were to zoom in, the IR formulas, well, this is again just basically a decay process, an exponential decay process. And like all of the exponential decay processes we've seen from the bacterial population and forward, it's just the size of the population divided by how long you stay on average in that box. And so, and that gives you recoveries per day. So that's going to mean that the infected population is going to have a link to recoveries. This is a negative feedback because there's an implicit negative link coming back. And again, this is basically just the bacterial outflow, but just with a different interpretation. So that's how we do that. And then we also talked about in that SIR model how we can do modifications to do scenario planning. And so we did this modification where we could change the total contacts per day with a lookup table that was based on the number of infected population. And so based on how many people were infected, then they could enact a quarantine, which would affect the total contacts per day, and then see how this lookup table affected the the results. And what we found, which is sort of a classic result, is that unless you quarantine super, super early, you will not change the total number of people affected very much. But what you do is you affect the transients, which is, in other words, the infected population. And so what we see is that if you don't quarantine at all, the number of infecteds gets very high. If you quarantine late, but at least sometime, the number of infecteds is a little shallower. If you quarantine early, then you don't have many infecteds at any unit time or at any particular time. And this is the so-called flattening the curve. That's where this comes from. The idea is that if you quarantine early enough, you're not focusing on reducing the number of affected people at equilibrium. You're trying to push the transient down. And as some of you work on your final projects, this is another thing you can look at. It's like, you might notice as you're moving your sliders around in your model, the outcomes at infinity aren't really changing a whole lot, but there might be interesting things happening in internal parts of your model that are the transients. So peaks are getting taller or shorter as you're in SyntheSim and dragging those sliders around. And in the SIR model, that's a really useful result, because that's sort of saying that even if it looks like the long-term outcomes are not affected by quarantine policy, the short-term outcomes, which turn into long-term outcomes if we include the effective hospital capacity, are being affected. So that was kind of the lesson there. So any questions about this SIR case? Okay. Then we moved on to growth and diffusion, so the BAS innovation model here. And again, we came back to the fish stock here where we got our net regeneration curve, but we tried to make this a little bit easier to see on a diagram. And so we said, well, you know, we could, instead of putting net regeneration inside a box here on its own, we can create a new stock called remaining fish capacity. And then we'll end up having the fish stock to birth rate will always be reinforcing. But then we're going to reduce the number of fish capacity. That will end up being a balancing loop. And so then those things together make it much clearer to see the two loops that contribute to the S-shaped growth. Whereas S-shaped growth isn't really as obvious in this. But we can generate exactly the same population dynamics with this structure as we can with that structure. But we have to now be clear that whereas this carrying capacity was its own variable here, now carrying capacity emerges from the initial conditions of this stock plus this stock. So the total amount of fish that can be in the fishery at any time is basically the sum of these two stocks. So whatever you set the initial condition of this to, plus whatever you set the initial condition of this to, that becomes the carrying capacity. So it moves around where we put our parameters, but in the end, I think this ends up being easier to reason about in order to predict that S-shaped growth curve. And that modification of our fishery allows us to now draw comparisons to like the SIR system. So really it looks like the remaining fish capacity are like susceptibles and the fish stock are like infectious. So it allows us to now draw connections across models, which is really good for transferring knowledge once we learn about one model into another model. And then it allows us to develop these other models like the BAS model of innovation diffusion, where we have adopters of a technology and potential adopters. And so whereas remaining fish capacity or like potential fish doesn't make a lot of sense, potential adopters of a technology does make a lot of sense. And so we can see the total amount of people who could possibly adopt are the number of adopters plus the potential adopters at any time. So this is exactly the logic we have up here. The only thing that is added to the BAS model is going to end up being the advertising process. Now, in the BAS model, it's a contagion model. So, if you look at this diagram, try to see the relationships between the SI process and the BAS model. So, how often do people with the technology bump into people without the technology? And how often does that cause people without the technology to start using the technology? It's exactly the SI process. And so making those analogies there. And then, but the new thing that gets bolted onto the BAS model is a way of getting those initial adopters out there. So as in the SIR model, we assume the initial infection is exogenous. It just comes out of nowhere. Suddenly the population, a few people get sick and then it starts growing. Here, we can't really hope that people just randomly start using a product. We actually need to sort of pay some of them to start using the product. And that's what advertising's for. So there's this loop here, which, you put in a little bit of advertising initially to get adopters over here. Your advertising effectiveness dilutes over time as the number of adopters go away. But as you get more adopters, word of mouth becomes the dominating growth process. And that's kind of what the BAS model was modeling. And then we could show you could bolt other things on top of the BAS model to create slightly more complicated models, but it all looks a lot like the SIR model. So any questions about growth models? Basic sort of structures that we commonly see in growth models? Okay. So we moved on to Unit F, where we're now talking about sectors, decomposing a system into sectors. We introduced the notion of tipping points, and then we talked about learning. So basically things like boundary adequacy, structural adequacy, and so on. So that started out thinking about oil. And, oil seems like a market, so it seems like it should be driven by microeconomics. This is basically a microeconomic balancing loop with a delay. You could, in theory, use as a basis for any economic model that's out there. But in reality, oil is more than just a simple market. It has not only the kind of basic players, but it also has these non-market players, non-free market players, the cartels, that have a swing producer that can more directly control oil price. And that's what was sort of modeled into there. So, maybe be familiar with this because it's kind of a useful case study. Yeah, sorry, I saw the question in a second. So know that, Saudi Arabia as a swing producer, they can affect the dynamics of this by dumping oil on the market or pulling oil out of the market. And that effectively allows them to control price so that you don't get kind of a fair market price of oil. You get a price that's being actively controlled by the ones that has control of the oil. Question? Okay. Oh yeah, I'm sorry. Quarantine? Mm-hmm. Right. Sure. It affects the infection peak. So if I go back to here, this peak is no quarantine. This is a quarantine at a lot of infected people. This is a quarantine with very few infected people. So when do you turn on the quarantine to to reduce the contact rate? And so this is more aggressive. This is less aggressive. This is not at all. And so the point that we're trying to get here is that the quarantine policy makes it so that at any instant of time, there won't be a large stock of infected people. And so quarantines in the simple SIR model are not about reducing the total number of people who are going to be affected by disease. That is really hard. You'd have to quarantine almost immediately because once the disease is out there, it's very difficult to get a disease that has an R naught that's greater than 1 from spreading. But what quarantines can do is affect the transients. And so that effectively makes it take longer to get rid of an epidemic. But at any instant of time, the number of people, so that's what this is being plotted. This is the number of people currently infected. And so the number of people infected at any instant of time can stay under a threshold, which might be like the number of hospital beds or something like that. Right. Yeah, you could view it that way. Is that quarantining does have a small effect on how many people escape via due to herd immunity, but the real effect of quarantining has to do with, as you say, if everybody gets it all at once, then the whole health system, even if a small fraction of these people have to go to the hospital, then that small fraction might be way more than the resources that are available. So by making it so that you spread people out so that some get sick a lot later than others, then you make it that although that means that the society as a whole has to deal with the epidemic for longer, at any instant of time, they always have enough resources to be dealing with it. And that's flattening the curve. Okay. Other questions that I missed? Okay. Back to. All right, so the oil model. And then we went into the public sector applications, our kind of last major kind of case studies here. Basically the city example here was an example of this modeling approach where you come up with a dynamic hypothesis for how you think, let's say, a city or a system works. From that dynamic hypothesis, you create stocks and flows that you can simulate. You then generate connections between those stocks and flows consistent with your hypothesis, and then you actually then do the simulation. So the simulation output will produce behavior over time, which you can compare to behavior over time in reality. And if they match, then that gives you some confidence that you understand how the system works. If they are totally different, then that gives you an idea that whatever you thought was going on in the system is probably not the full picture, or might be the totally wrong picture. And so that's kind of a process to sort of build up an understanding of these kind of underlying processes that are in these systems that might be hard to observe. So you have to come up with an idea of what you think is going on in those systems. And the example we had here was that, well, here's our dynamic hypothesis of city growth as a CLD. And we go from the dynamic hypothesis here to building our question is what causes the rise and fall of cities. Hypothesis, these are the factors that can explain the rise and fall of cities. Prediction here is an output from a sim we built from this hypothesis. And test, we take those simulation results and compare them to reality. And based on how they work, we either update our hypothesis or we make use of our hypothesis to do something hopefully useful in the real world system. And so we showed how we can go from those CLDs to building these complex models, to building these complex webs of connections, and then producing outputs like these, where these are real data here, and this is simulation data. And one of the nice things about these simulation data is not only do they kind of match the rise and leveling off that we see in real cities, but if we look closely, we can see that labor and worker housing are leading indicators of everything else. So that might suggest that labor and worker housing are the things that's ultimately underlying the eventual slowdown of city growth. And this, I think, is even very relevant as we talk about, like today, how California is starting to add a lot more rent control and so on, because it's hard for people, worker housing, it's hard for workers to afford to live near where they want to work. And so one approach to that is to limit the rent. But that has downsides because that can actually make less incentive to build more housing. That can make housing kind of go into disrepair and so on and so forth. And so this kind of drives home that, yeah, worker housing is super important. And there are short-term solutions that may have long-term problems, And, and we could then start adding those things in. So this is our as is system. And now we could add rent control and see what happens in the short term and in the long term. We might get more growth in the short, more sustained growth in the short term, but then we might get crashes. So whereas this sort of flattens out, this doesn't crash very much, there might actually be even larger crashes if we implement something like a rent control system, and we could test that in the model. So that's kind of how the process would go. All right, so are there questions about this, about explaining complex phenomena? It's kind of like similar to in the fisheries here, where you can where we can't see under the water, and so we use a simulation to sort of give us an idea of what might be going on under the water, and it gives us new insights into the dynamical the behavior of the things we can see. Okay, questions online? All right, so then that gave us the opportunity to talk about tipping points. I want to make sure everybody knows about tipping points and how they're characterized dynamically. So this is a term that's kind of thrown around similar to chaos, that where some of the things people call tipping points aren't actually tipping points. Tipping points are very sort of specific. So in this kind of example here, you can imagine I can tilt the floor or I can tilt the refrigerator. And some people mistakenly would refer to tilting the refrigerator too far while leaving the floor here as it reaching its tipping point, because that's where the refrigerator kind of tilts over. And that's not technically a tipping point. A tipping point is about a parameter which makes a system more prone to be able to switch from one equilibrium to another. I know that I can always tip this refrigerator over onto its side, and I know I can always set it upright. And that's sort of not that interesting. What's interesting is the thing the refrigerator's sitting on. As I tilt it upwards, it kind of narrows the gap between the upright position and the on its side position. So the tipping point is the point at which the ground is angled so much that the refrigerator ceases to be able to be in this position and moves over into the other position. And then when you move the ground back, then the refrigerator, it's like a totally different refrigerator. So to kind of illustrate that, if I tilt the ground, I can bump on the refrigerator a little bit, it stays upright. If I keep tilting the ground, eventually I get to a point where this is the so-called tipping point, where the center of gravity of the refrigerator is over the corner of its foot there. So if I bump this just a little bit, then it will tip over. But now if I move the ground back to where it was to start with, I'm in a totally new system. So the point there wasn't that I tipped the refrigerator over. I mean, that's certainly important. But the point here was studying the angle of the ground. How much can we tolerate putting a refrigerator on an angled ground? And we have to be careful if we keep angling it, because if we ever do finally cause the refrigerator to tip, then when we go back to what we thought was a safe position, it will be a totally different system sitting on top of that. And so we've now flipped the system into a different mode. And that's kind of, about tipping points. So in order to get things back, I might need to change my parameters into a range that I've never even lived with before to get the system fixed again. And so that's kind of our tipping point. So the tipping point in this system was the angle just before the refrigerator tipped, and required a new strategy for management. So before the ground was at this angle, we could manage the refrigerator one way. After the ground reached this angle and the refrigerator tipped, we had to come up with a totally new strategy. Just like in the fisheries example, once a fishery has gone over its tipping point, you can't just go back to a previously sustainable configuration. You've now got to basically get rid of all the ships and wait for the fishery to recover before any ships can come back. And that's the danger of crossing these tipping points. And so that's what we illustrated with the fishery example here. We had a number of ships. So make sure you can read these graphs too. A number of ships at sea, the catch that they have here, the regeneration rate rises to the catch. You have a sustainable outcome. But So you raise the number of ships farther, which raises the catch farther. You have a new sustainable outcome as things come together, and that's great. But then the downside is if you keep raising the number of ships, then eventually you get to a point where you cross over this tipping point. So at a low number of ships, fish regenerate at this rate. You increase the number of ships, so you're asking for this many. So the fish density decreases, and that raises them up to this rate and comes into balance. So then you increase the number of ships even further. And that's going to cause the fish density to go down because now you're pulling out at this rate, but they're only regenerating at this rate. So fortunately, they increase. Now they're at the maximum rate that they can put out there. So this is our so-called maximum sustainable yield. And so if we end up raising the ships even a little bit farther, then now there's no room for the regeneration rate to increase. And so the density is just going to keep decreasing. And as the density decreases, they actually regenerate even slower, which causes the density to decrease even faster and faster and faster. And so at this point here, if you go back to the previous level of ships that used to be sustainable, you're now still above the regeneration rate that the fishery can support. So really, your only option was to bring the ships down to where they're at this regeneration rate or lower, so that the fish can then recover and get back to where they were. So, that point, that was the tipping point for this system, where the density crossed from the right-hand side to the left-hand side of this regeneration curve. And that maximum sustainable yield, it's roughly half the carrying capacity. It's like the maximum amount of biomass you can remove from the bank that is the fishery before you go from borrowing from principal to borrowing from interest to borrowing from principal. And so that's kind of what we're saying there. And so in our behavior over time plot, once we raise the catch rate up to this point, the regeneration rate tries to reach it, but it can't, because this is the maximum rate that they can regenerate. And so it crosses that tipping point and the regeneration rate collapses. So the fish stock doesn't level off, it collapses. And even as you drop the number of boats back down to the previously sustainable level, this catch rate is still higher than the regeneration rate. And so the fish stock just continues to collapse into extinction. So that's an example of tipping points where a system that used to be we used to be able to operate at this level totally fine. We went over the tipping point and now we can't operate there anymore. That's what makes it a tipping point. So any questions about that, about tipping points or this example with the fishery? It's just sort of emphasizing this stuff. Okay. This is just saying that. So the other analogy which might be helpful if you think about a wine glass, eventually once it tips over, everything spills. And so even if you can set the wine glass back up, you'll never get the wine back in. And that's an example of an irreversible system. And there's a bunch of these tipping points that are irreversible that are in world systems, which is why it's so important not to tip them, because you can't just shift back to some other policy and wait for the fishery to recover. Sometimes they'll never recover. You know, sometimes the aquifer will never refill. Sometimes the ice will never reform exactly where it was before. And so climate change is a great example for tipping points, also political instability. So you can imagine somebody's willing to be, willing to tolerate a bad government for so long. But once you start a rebellion, the genie can't be put back in the bottle. Attitudes and social norms, there can be good tipping points. You can spend a lot of money trying to get people to recycle. And if they reach a tipping point, then maybe when you stop spending money advertising recycling, people continue to recycle. So in the previous version, you weren't spending any money advertising recycling and no one was recycling. They go through a tipping point, and now you go back to not spending any money advertising recycling, and yet people are recycling. So that's our tipping point. So Any questions about tipping points? Or anything else that's, you've thought of? We use tipping points to motivate the idea of a bifurcation diagram, which is a great way to summarize things like tipping points, which really require you to experiment with a wide range of parameters in a dynamical system. So you can put a parameter like harvest rate on the x-axis, and you can simulate it for a wide range of initial fish populations, and then see where things go as time goes to infinity for each harvest rate fish population combination. And what you end up getting is so this is what I'm just saying here is you end up getting a diagram which helps you actually see where the tipping points are. So like in our fish example, I know that at this harvest rate, there are two possible steady states, one at this fish density, one at this fish density, or one at one population, another. And I know that this middle fish population is what I'm going to say is unstable. So if you add one fish to it, it'll go to the one on the right. If you take one fish away from it, it'll go down to extinction. I know that this upper fish population is what we refer to as stable. If you add one fish to it, it'll come back. If you take one fish away, it'll come back. And I know that the extinction equilibrium is also stable, because if you somehow add one fish when there's no fish in the fishery, it won't survive very long, so long as you're harvesting at this rate. So I can take all three of those things and plot them together, and I can do that for all of my harvest rates. And I end up generating a curve that looks like this one. So where I've got my stable equilibria up top and down bottom, and this unstable equilibria, which is kind of like a mountain ridge in the middle. So this is like a valley here and a valley here and a mountain that's in between them. And so we can navigate around the mountain in order to get to these different equilibria. So we can be totally fine in this valley, but if we go too far and then get stuck on this side of the mountain, we're naturally going to roll downhill into this valley down here. And so this explains that while this here is a tipping point where if we push the system far enough, we don't have any more valley left over up top. And so we're stuck rolling into this valley, and there's no easy way to get back to that valley unless we can manage to climb over that mountain again. And so that's kind of what I kind of depicted during that lecture, is that we've got this sort of idea here of starting at some initial condition, and where you're at this harvest rate and this fish population, going to a different harvest rate, which pushes us into this region where there's no mountain separating us from the extinction. So then we naturally start floating towards extinction at this upper harvest rate here. And once we're in this region here, even if we lower the harvest rate, we now have no way to get over this mountain ridge, and so we just keep falling towards the extinction valley. So the only way we can get back up to this valley is if we go through the hard work of crossing this mountain, and that means reducing our harvest rate down to so low that we manage to get over this mountain, so that we can roll down the other side of the mountain, get back up to the stable valley, and then we can start increasing our harvest rate so that we're back to where we started. And so that's a bifurcation diagram, summarizes a lot about a system. So any questions about these bifurcation diagrams? These are often drawn in mathematical systems, but you can also generate them numerically with your simulations. You just have to pick a parameter and pick a bunch of initial conditions and see where things go to steady state, and then plot all of that out for every one of those combinations. And then you can generate a plot that looks like this one, with blue regions and red regions and so on. Okay. All right, so we're getting kind of towards, and this in general is a process called hysteresis, history dependence. And that's what tipping points often create, is a dependence in the history of the system. All right, so So we're kind of running out of time here. I've got, just if you're willing to run through these slides afterwards, and if you have any questions, you can send them to me. But basically, again, I've just sort of sampled from a bunch of these slides. I will say that these slides here about endogenizing, we didn't actually get to this, so I don't think I have any questions on the final exam about endogenizing exogenous variables. But if you're interested in that, we did. In the fishery chapter, they do talk about that. How do you make it so that the model picks the number of ships as opposed to the modeler? And that's what we refer to as endogenizing. But like I said, the rest of it is just kind of the greatest hits of the rest of the things here. So if you have any questions, I'm happy to take them now. If you want to come up after, I'm also happy to take that. If anything comes up between now and tomorrow, I'm happy to take your questions over email. But otherwise, that's kind of all I've got for you today. Again, the things open up Wednesday, Thursday, Friday for stage 1, Monday through Friday for stage 2 next week. And I'm not going to do an attendance question today. All right, well, in that case, I will be here Thursday, but you don't have to be, but feel free to come in if you want to take your stage 1 here. Anything else comes up, just send me a note. Looking forward to seeing your projects tomorrow night. And don't forget about the muddiest point on Sunday, your last muddiest point. Any questions online before I cut the feed here? If not, then I'll go ahead and stop the recording and end the meeting.